Hi friends, just like you live in a house which has a street address, a street number, your floor number and flat number, similarly electrons also live in an atom and they have addresses too. They live in orbitals and their address is given by quantum numbers. So what are these quantum numbers? What is the quantum model of the atom? What is Schrödinger's wave equation? We are going to look at all these exciting quantum concepts in this video. And I'm going to explain it with a very simple house analogy so that you'll find quantum numbers as easy as your house number. So make sure you watch the video till the end. And before we begin, I'd like to let you know that do check out the courses on our website manochaacademy.com and our Android app. To make it easy, I'll put the links below. So let's dive into our quantum world and quantum numbers. As we have discussed in the previous video, the scientists have proposed different models for the atom over the years. It all started with Dalton proposing the atom to be like a solid sphere. Then you had Thomson's plum pudding model, followed by Rutherford's nuclear model. And then those drawbacks were corrected by Bohr's planetary model, where the electrons revolve in certain orbits. And then finally we have the quantum model of the atom proposed by Schrödinger. In this video, we are going to be looking at what is this quantum model of the atom, also known as the quantum mechanical model or the wave mechanical model. So we are going to discuss the quantum model and I'm going to make it absolutely easy for you. So let's dive into it. So what's the difference between Bohr's model of the atom and the quantum model? There are some major differences. There are some major improvements. So let's talk about that. First, let's look at Bohr's model. Remember, Bohr said that electrons revolve around the nucleus in certain fixed orbits, what are called shells or orbits. And the radius of these orbits are fixed and electrons are moving with a fixed amount of energy and with a fixed velocity. So all these orbits have a certain energy, so we say the energy is quantized, and when the electrons revolve in these orbits, they are not losing energy. So they will not collapse into the nucleus, and he resolved the drawback with that Rutherford's model had, that he could not explain the stability of the atom. But with Bohr's model, we can now explain the stability of the atom because electrons revolving in these fixed orbits, they do not lose energy. But then there were some major changes, like de Broglie proposed that electrons have both wave and particle behavior. We know electrons are particles, but they also have a wave-like nature, which was proved with the famous experiment. So if you want to watch those details, you can check out my video on de Broglie's hypothesis. And then there's the Heisenberg uncertainty principle, which said that you cannot simultaneously determine the exact position, right, and the momentum of an electron. So this whole model where electrons were thought to be these tiny particles roaming around in fixed orbits, that went away. And now we have the quantum model, because in Bohr's model, electrons were revolving in these fixed 2D orbits, but quantum model took a more 3D view of the atom. And it said that electrons are not just particles, but they have a kind of wave-like behavior. They are spread around this nucleus, and the goal of the quantum model is try to predict, where the electron is. That is, what is the place where we can find the electron with the highest probability? Because we know that the electron is having this kind of wave-like behavior, so it is like sort of spread everywhere, but we are trying to predict where it has the maximum probability. So that is where the quantum model is very different, very interesting. It recognizes the wave-particle duality of electrons. It acknowledges Heisenberg's principle, and the goal here was to find that, okay, these electrons are roaming around the nucleus, but where exactly they are. And this is where the scientist Erwin Schrödinger came in, and he solved this difficult problem of finding the maximum places where the electrons have maximum probability. So let's talk about Schrödinger's wave equation. As we discussed in the quantum model, the electron is regarded both as a particle and a wave. So it is like this matter wave that is going around the nucleus. And the scientist Erwin Schrödinger found the equation, the mathematical equation to describe this electron wave. So what is that equation? It is this difficult equation involving some complex mathematics. So we are not going to go into the details here, but I can tell you that this function, this psi t, is basically your wave function. This symbol is called psi, and it is the wave function describing the electron. So if you solve this difficult equation, right, we are not going to go into the solution for that. It's really complex, and that is why Erwin Schrödinger won the Nobel Prize for this equation. So if you solve this equation, the solution of this equation gives us three variables. And these three variables represent the positions where the probability of finding the electron is maximum. Because remember, the electron is like a wave, so we cannot tell exactly where it is, right, at any given time. Even if we can tell the position, then we can't find its momentum accurately. All those complexities with Heisenberg's principle, remember? So we want to describe it by this probability function, or we call it as a wave function, right? And our goal is to find where the probability of this electron in the atom is maximum. So solving this equation gives you that. So we cannot find the location exactly, but we can find where it is likely to be, right? Where the probability is highest. And when you solve this equation, you get three variables. These three variables were labeled as N, L, and M. And these three variables are called the three quantum numbers. So these are called quantum numbers. So if you know the values of these quantum numbers, you know where the electron is likely to be. There is also a fourth quantum number we'll talk about, but the solution of this gives you these three quantum numbers. So let's look into quantum numbers. So what are these quantum numbers exactly? To put it in a very simple way, they give you the address of the electrons, where the electron is likely to be found. Just like you have a house address, right, on which number in the street you live in, then what is your flat number, right? So you have an address which is denoted by these numbers, and it's not 100% sure we'll find you there in the morning, but we are likely to find you in the morning, or let's say late in the night, okay, or you may be out. Similarly, these quantum numbers are the numbers which give you the address of the electron where it is likely to be found. So what are these quantum numbers? Remember, there are four quantum numbers that are used to describe the position or the location of the electrons. And they are called the principal quantum number, the first one. It is denoted by the letter N. So principal, you can remember the most important quantum number, like the principal of your school. So this is principal quantum number denoted by N. Next is azimuthal quantum number. This is denoted by the letter L. And you can remember azimuthal has L in it. Next one is magnetic quantum number. So it has the letter M in it, and it is denoted by the symbol M. These are all written in lowercase. And finally, we have the spin quantum number, which is denoted by the letter S. So we are going to discuss these quantum numbers in details and understand what do they mean, what do they represent. But remember, in a basic sense, they are giving you the address, the location of where the electron is likely to be found. And as we discussed, they are the solutions of Schrödinger's wave equation, the first three ones, right? N, L, and M. So remember, in Bohr's atomic model, the electrons were revolving in fixed orbits. But in the quantum model, we are taking a totally different view. And we say that electrons are moving around the nucleus in what we call as orbitals. So we are basically going from orbits to orbitals. In Bohr's model, we had these orbits. In the quantum model, we say that electrons are moving in orbitals. So that's why we are using this different term to differentiate these. And these quantum numbers are describing these electron orbitals. So these quantum numbers are basically used to describe the orbitals of the electrons. So you can visualize the orbitals as the space in which the electron is moving or it is likely to be found. Because remember, again, it's all about probability. So we are trying to say that, okay, most probably this electron is going to be found in this region, which is called an orbital, and it is described with these quantum numbers, these 4 quantum numbers. So let's discuss these quantum numbers in detail, starting with the first one, which is the principal quantum number. The first quantum number that comes out of Schrödinger's wave equation is called the principal quantum number, and it is denoted by the letter n. This variable n can take on values such as 1, 2, 3, 4, 5 and so on all the way to infinity. So you can see it can take on positive integer values. So what does this principal quantum number represent? Principal quantum number is basically representing the size of your orbital. So we can write over here, it represents the size of the orbital, the space in which the electron is located. If the principal quantum number is small, like 1, that means the size is small. So 2 is bigger than 1, 3 is bigger than 2 and so on. So we can see that as the principal quantum number increases, the size of the orbital will increase. So we can say that the electron is moving in a larger orbital, in a larger space. So this is the actual meaning of the principal quantum number. But to make it easy, to make our visualization easy, we say that the principal quantum number is really representing the shell, or we call it the shell number, right? So it is, for example, the quantum number 1 is representing the K shell. So we are trying to relate it with Bohr's atomic model, right? Because that model we have been using for a long time, we are familiar with it. So we are trying to make this analogy, okay? But remember, this is our simplification, because actually there is no single shell in the quantum model. So number 1 represents the K shell, number 2 represents the L shell, number 3 represents the M shell, then N shell, and so on. And this you are familiar with, K, L, M, N shell. And you know that as the shell number increases, or as you go down the shells, the shell becomes bigger because you're moving further away from the nucleus. So it is a good analogy, and you can remember that principal quantum number, roughly the n is representing your shell number, but it's actually representing the size. Now what about the energy of the electrons in these orbitals, right? So as you increase the principal quantum number, that's right, the energy also increases. So this energy also increases. So if you are in a shell or in a region, I'm saying shell, right? So if you are in this region, this orbital which is close to the nucleus, like it has a quantum number of 1, the principal quantum number of 1, that means the energy is less. But if the electron is in the orbital with principal quantum number 4, the energy is more. And we have done that formula in Bohr's atomic model. Remember, we looked at the formula of energy. Energy is minus 13.6 Z square by N square, where Z square is the atomic number and N is the shell number. So see, as the shell number increases, this number will become smaller because it's in the denominator, but there's a negative sign there. So smaller negative number means larger energy. Okay, so this is matching what we have done in the Bohr's model. So always we'll try to do some relation here and see what is the analogy with Bohr's model. But again, remember, this is a completely different model, and we are trying to describe this new concept of electron orbitals because the shell no longer exists. But this is a nice simplification which will help you understand it. So remember, principal quantum number is actually representing the size of the orbital, but roughly speaking, it is representing the shell. So we have talked about the first quantum number, which we roughly said is basically our shell number. But to understand all the remaining quantum numbers, let me explain it to you with a very simple analogy. So we are going to imagine that electrons, they don't live in orbitals, but we are going to put them in houses. So yes, we are going to be the architects of the structure of the atom. So let's say that we are going to put these electrons into houses, and these quantum numbers will give us the address of the electrons. Okay, so we'll start off with, let's say these are the houses that we built for the electrons. So this is house number 1. The smallest house is house number 1. The next house is house number 2. third house is house number 3, and this is house number 4. So this 1, 2, 3, 4, you can see this is basically associated with our principal quantum number. What we were saying is the shell number, right? So again, as we said, that as n increases, that orbital size increases, or basically here our electron house size increases. Okay. Now, when we go to each of the houses, we will divide them into levels or floors. Okay. So since the first house is very small, we'll just keep it at one level. So let's say there is just level 0 in this house. Okay. And the level numbering we will do from the top. So I'm going to label that as level 0. Now since the second house is bigger, we are going to split it into 2 levels, 2 floors, right? So this is level 0, and the bigger one I'm going to label as level 1. Okay. So it's not a 0, 1, it is 0 from the top. Same way over here, the third house is broken down into 3 levels, and we are going to label it starting with the number 0. That is the convention which we are going to talk about when we look at the other quantum numbers. Okay. So not 1, 2, 3, 0, 1, 2. And what will be your labeling for the last house? 0, 1, 2, 3. So see, every level is marked here. This is like our next quantum number, which we'll be looking at, the azimuthal quantum number. So it is sort of representing which level, which floor the electron is in. Now, as you're the architect, every floor is going to be divided into rooms, right? Because we are building a house. So every floor we are going to split it into rooms. But obviously, it depends on the size of the floor, right? So how many rooms do we split it in? So you can see the first house is very small. It has just 1 floor. So we can say, okay, let's put just 1 room in this house. The second house on the 0th floor, this floor, since it's small, just like the first one, it's just going to have 1 room. But this floor, floor number 1, is pretty big. So I'm going to go ahead and split it into this sort of, you can think, equal size rooms over here. 1, 2, 3. So you can see we have 3 more rooms here for the electrons. So we still haven't filled in the electrons, hold on to that. And each of these rooms will have a room number, right? Because we have to give the address of the electron, where it is located. So you have given the house number, you have given the floor number. Now we can talk about the room number. How do we label the room numbers? So we'll say that these middle rooms, it's like the number line, right? The middle rooms have a room number of 0. The ones on the right have +1. The ones on the left have -1. So it is like 0, +1 and -1. Okay. So that means this room is basically in house number 2, level number 1 and room number 0. This room is house number 2, level number 1, room number +1. This is room number -1. Is the concept getting clear? So basically what we are doing is we are dividing our houses, the orbitals, into compartments where we are going to fill in electrons, into parts, you can think. Okay. Same thing we are going to do with house number 3. So house number 3, what will you do? Same thing, you draw this kind of triangular pattern. So this is just enough space for 1 room. So we'll leave it like that. The floor number 1, the second floor from the top is bigger. So we are going to split it once again into 3 rooms like this. This one is even bigger. So again, I'm going to draw this pattern and split it like this. So nice design we have. So here you can see the 0th level has just 1 room in it. Level number 1 has 1, 2, 3 rooms in it. Level number 2 will have 1, 2, 3, 4, 5. So it's always an odd number of rooms. 1, 3, 5. Again, just like in a hotel, how do we get the room number? The room numbers are once again given like this. The middle rooms have a room number of 0. The ones on the right have a room number of +1. The ones on the left, -1. This one on the right, +2. This one will be -2. So this is basically telling you the room number in which the electron can go. And then let's go to our finally the biggest house. So here once again you have to play like patterns. So draw the rooms and now you'll get the idea. It's very easy. You just have to draw these triangles. So just draw these triangles like this. There you see. And there you go. So you can see larger the level, the more rooms obviously it will have. So our houses are like this beautiful triangular kind of houses, our orbitals, and we have divided them, so this entire shell or house into these different orbitals here for the electrons, into these different rooms. And so here you can see once again the room numbering will be done this way. So you have 0, +1, +2, +3. So this is, all these room numbers are +1. This is +2, these room numbers, and this will be +3. You guys get the idea? Same with these room numbers will have an address of -1. These one will have an address of -2, these guys, and the last one will have an address of -3. See, we are needing how many numbers here? 3 types of numbers. One is the house number, right, which we are calling is the principal quantum number, the shell number. So that is telling us which house the electron is in. Then you have the flow number, which is going to be your azimuthal quantum number, represented by L. So the pink guys are basically your L's, or the level, you can remember which level it is in, right? So this is like level of 0, 1, 2, 3, and so on. And then finally, you have these. Oh, I forgot to put in this one. So since there's just one room, it will have a number of room number 0, okay, because there's just one room. So all these green numbers are what is called the magnetic quantum number. You can say the room number. So room has M in it. So these are basically your room numbers, M, okay, and they can take on these values. And in each room, how many electrons can you have? So electrons are sharing, guys, here. Every room is double occupancy. Each and every room can hold 2 electrons. So basically, you can say that each room in this house, so for example, in the first house, there can be 2 electrons. So I'm going to draw them with the help of these lines. So every room is going to have 2 electrons. And we'll see why we've drawn it with those up and down arrow, because there's a clockwise, anti-clockwise spin of electrons. We'll come to that. So but basically, you need to remember every room here can hold 2 electrons. And so you can say that if you want to know which electron it is, you can say that is it on the left side or the right side, right? Or clockwise spin or anti-clockwise spin. And that is why that is the last quantum number, which is the denoted by S, the spin quantum number. So every room here is having the capability of holding 2 electrons and so on. So this double arrows that I've shown here is basically representing the pair of electrons, 2 electrons. Clear? So if you remember this simple analogy, that quantum numbers are giving the address of the electrons in the orbitals, in the atom. And so you can remember that this is like a house address. So for example, if you want to know, let's take an example. Where is this electron? Where is he located? He is in house number 2, okay, floor number 1, room number -1. And if you want to talk about the left one, then he is the left side, or maybe with a clockwise or anti-clockwise spin, right? So let's say he has a clockwise spin here. So this is exactly what are quantum numbers. They give you the address of where the electron is likely to be found or likely to be located. Let's take another example. What will be the address of an electron, let's say, in this quantum number? Sorry, in this room. What will be the address of this electron? He is in house number 4, so principal quantum number 4, level number 2, right? He's in level number 2, so that's our azimuthal quantum number, magnetic quantum number of 0, right? And this is the electron, let's say it is having a anti-clockwise spin, okay? So that is the guy on the left here. So using these quantum numbers, N, M, so what are our quantum numbers? The principal quantum number N, which is sort of representing your shell, okay? Your next quantum number L, the azimuthal quantum number, is representing which floor you're in. So that is like subshell, okay? And then which room you're in, or within that level, which orbital you're in, that is represented by your magnetic quantum number. It's representing which room you're in here. So this N, L, M and S are basically your 4 quantum numbers. So if you remember this interesting analogy, the remaining stuff will be much easier for you. You'll be able to correlate it. And so this representation you can remember to understand that why we need these addresses. What are these quantum numbers? And as you can see that as the principal quantum number is increasing, the house size is increasing. It can fit in more electrons as we expect. So let's take a look at our second quantum number in more detail, which was the azimuthal quantum number. So our second quantum number is called the azimuthal quantum number, and it is represented by the letter L. So this is basically the letter L represents it, and it is also known as the angular momentum quantum number, because as we'll discuss, it will give you the angular momentum of the electron. So what is this azimuthal quantum number representing? In our house analogy, as we saw, it is representing which floor you're in, right? So n was the house number and in which level or which floor you're in. So roughly speaking, azimuthal quantum number gives you the information of the subshell, because we can think a shell is divided into these levels or subshells. But in reality, it is describing the shape of the orbital, because different orbitals have different shapes. Okay, so let's discuss about the shapes of the orbitals. So as we said, the azimuthal quantum number, the floor level number, takes on these values like 0, 1, 2, 3 and so on. Okay, and this depends on which shell you're in. So if you're in shell number 1, it can have only one level because it's the smallest shell, 0. If you're in shell number 2, it can have these two levels, 0 and 1. If you're in shell number 3, it can have 0, 1, 2. If you're in shell number 4, 0, 1, 2, 3. So what is the pattern we are seeing, guys? We can see that the azimuthal quantum number basically is greater than 0, okay, and it is less than equal to n minus 1, where n is basically your shell number or basically the principal quantum number. So azimuthal quantum number is always greater than or equal to 0. It starts from 0 and goes all the way up to n minus 1. Now what are the shapes here? So we say that the first azimuthal, if it's in the first orbital, which having a L of 0, the name given to it is S, and you can remember S stands for spherical. This is a spherical shaped orbital. So it has a shape of a sphere. The next one, azimuthal number 1, it has a label. The scientists have given this label P, and it is the shape of a dumbbell. Okay, it is this kind of dumbbell shaped. Then if you go to azimuthal quantum number 2, L is 2, it is given a name D, and it has a shape of a double dumbbell, right? The next one, L is 3, it has the name F, and this one is even more complicated. It's an 8-fold structure, so usually you don't have to worry too much about this. I've just written here, it has a very complicated shape. And we can go on and on, right? So azimuthal quantum number M, the next one is 4. This will have a label of G, and it will have another complicated shape. So what do I mean by this shape of the orbital, which is represented by the second quantum number L? See, different orbitals have different shapes. Like I told you, the S orbital, that is when the azimuthal quantum number is 0, it has this kind of spherical shape. So electron roams around in this kind of spherical shape for this orbital. When azimuthal quantum number becomes 1, so for L equal to 1, it has this kind of a dumbbell shape. Can you guys see? It will have this kind of a dumbbell shape. Okay, so it will roam around in this kind of manner. For azimuthal quantum number 2, the orbital becomes even more complicated. So it has this double dumbbell shape. Okay, so the electron can roam around in this kind of shaped orbital, and this is called the d orbital. So remember, n was giving us the size of the orbital. The next quantum number gives you the shape of the orbital, what kind of shape it is in. In our analogy, we were taking it as a subshell or a level, but in reality, it is a shape. So you'll always have to keep switching back and forth here in the analogy that yes, azimuthal quantum number is sort of roughly representing the subshell, but it is really the shape of the orbital, as we can see here. And remember, Azimuthal quantum number goes from 0 to n minus 1, where n is the shell number or the principal quantum number. So we have talked about principal quantum numbers and azimuthal quantum numbers. Principal quantum numbers, remember, are denoted by the letter n, and they're sort of roughly representing the shell number. So 1, 2, 3, 4 and so on. And in reality, they are representing the size of the orbital. Azimuthal quantum number is representing the shape of the orbital, and it is denoted by the letter L. And we saw it can have values from 0 to n minus 1. So for the first shell, it will have value 0. For the second shell, it will have value 0, 1. For the third shell, 0, 1, 2. For the fourth shell, 0, 1, 2, 3. So if we say the electron is in the first n equal to 1, first shell, and this is like our subshell and the 0th subshell. So we can say electron is in 1, 0, but rather than writing it this way, we write it as 1s, because remember, we gave this labeling that for the azimuthal number, quantum number 0, the label is s. For 1 it is p, for 2 it is d, for 3 it is f. So we can say 1, 0, basically the address is 1s. Similarly, if you have an electron in the third shell and in the azimuthal quantum number 1, what will you call it? Rather than saying 3, 1, we say, hey, it is in room number 3p, or it is in orbital 3p. So these are the possible combinations, right? So for the first shell, you have 1s. For second shell, what are the two possibilities? 2s and 2p, right? 0, 1. For the third shell, it is 3s, 3p and 3d. For the fourth shell, it is 4s, 4p, 4d and 4f. So basically, when you look at these combinations, this tells us which subshell or which level in our house it lies in, right? So 1s means you're in the 1s subshell, shell number 1 and subshell s. If you're in 3d, then you're in shell number 3 and subshell d. So going back to our house analogy, basically the principal quantum number and azimuthal quantum number tell you that which floor, which level are you in. So if we are in 3d, that means we know we are in house number 3 and level 2. So the electron is somewhere here, right? We don't know which room, but somewhere here. Same way, if it is in 2s, that means it is in this level, 2 and azimuthal number 0, because 0 means it is s, okay? So this is what these azimuthal and principal quantum numbers together represent. Now let me ask you a question. What is the number of subshells in a shell? What is the meaning of subshell? Remember, subshell is represented by our azimuthal quantum number. So we say subshell, or basically the shape of the orbital. So how many subshells are possible in a shell? Because remember, this n is representing your shell and azimuthal quantum number is representing which subshell it is in, right? So if you take a look, can you see that the first shell has only one subshell? The second shell has two possible subshells, right? Or you can look at this way, 2s, 2p. The third shell has three possible subshells, 3s, 3p, 3d. Fourth shell has four possible subshells, 4s, 4p, 4d, 4f. So can I not say that the number of subshells in a shell is equal to n, which is equal to the shell number, right? So basically, bigger the shell, it will have more subshells, which is equal to the shell number. Bigger our house, more floors in it. Same logic, right? So this very important relation, that number of subshells in a shell is equal to n, because remember the azimuthal quantum number L goes from 0 to n minus 1. So since we are including 0, it's basically 0 to n minus 1 basically means it is n number of subshells, right? That is your inner shell. So that is what is represented by our azimuthal quantum number, or the quantum number for the angular momentum quantum number. The azimuthal quantum number is also called the angular momentum quantum number. Why? Because it helps us to find the orbital angular momentum of an electron. So what is the formula for that? To find the orbital angular momentum, the formula is h by 2 pi, where h is Planck's constant and L is your azimuthal number. So it's square root of L times L plus 1. So here L is your azimuthal quantum number. Okay, so let's see how we can apply this formula. Let's say we want to find the orbital angular momentum in the 3D subshell. Remember, this azimuthal quantum number is representing your subshell. So when we talk about 3D, this subshell 3D, what is the value of L over here? So remember, we had done this list. L takes on these values 0, 1, 2, 3. And what are the names that we gave it? 0 is called S, this is called P, this is called D, and this is called F. So usually 4G we usually don't deal with, right? So here, if we have 3D, that means the value is going to be 2, right? The D subshell means L is equal to 2. So I'm going to substitute the value here. So for L equal to 2, let's plug that into this formula. So our orbital angular momentum is going to be equal to h by 2 pi square root of L. L is 2 here because it is D subshell, right? So 2 times 2 plus 1. Okay. And so let's simplify that. So what do we get here? This is basically going to give me h by 2 pi multiplied by 2 times 3. So that is square root of 6. So this is our final answer, and you can see why it is called angular momentum quantum number, because it helps us to find the orbital angular momentum of an electron using this formula. This is an important formula, so note it down and remember it. So we have looked at the first two quantum numbers, which was the principal quantum number and the azimuthal quantum number. Now let's take a look at the third quantum number, which is called the magnetic quantum number. It is represented by the letter M. So remember, the principal quantum number was representing the size of the orbital. How large is the orbital? The azimuthal quantum number was representing the shape of the orbital, whether it is spherical, dumbbell, double dumbbell, and so on. And magnetic quantum number M represents the orientation of the orbital. For example, is it in the X direction, Y direction, or the Z direction? Because remember, the atom is in 3D, right? So the orbitals can be aligned along any of the axes. Okay, so remember, magnetic quantum number represents the orientation, in which direction the orbital is oriented. So with the help of the magnetic quantum number, we can find the number of orbitals present. Because remember, what was our analogy? Principal quantum number is the shell. Azimuthal quantum number is the subshell. And in the subshells, you have these orbitals, which were represented by the magnetic quantum number. Just like our house, levels, and then now we go down to the rooms in the floors or the levels. Okay, so let's take a look what this magnetic quantum number, what values can it take? So the rule is magnetic quantum numbers takes on integer values from minus L to plus L, where L is the azimuthal quantum number, right? So L was our azimuthal quantum number. So using the value of L, you can get the values of M. Let's understand this with an example. So if we look at the L value of 0, that means we said this is the S, it's called the S orbital. What can be the possible values of M? M can take on values from plus 0 to minus 0, so basically 0. So here you can see the only possibility is 0. That means in the S subshell, you have only one orbital. Okay, so we can represent it by one box. So we can represent it as one box like this. Okay, obviously in reality there's no boxes, it's all in space, but just like we had that rooms, so I put one room over here. Next, when we look at azimuthal number of 1, that means it is the P subshell. In the P subshell, you can have values from minus 1 to plus 1, integer values. So the possibilities are minus 1, 0 and 1. So how many M possible values are there? 3. That means there are 3 possible orbitals over here. P subshell. In the P subshell, you have 3 possible orbitals. Next, let's look at the azimuthal number of 2. So in the subshell 2, which is the d subshell, you can have 5 possibilities, because from -2 to +2. So the d subshell contains 5 orbitals. So I can draw 5 boxes over here, right? So these are like your 5 rooms for the electrons. And now looking at azimuthal number L equal to 3, that is the F subshell, we can have these possible values from -3 to +3. So basically, how many orbitals are possible? 1, 2, 3, 4, 5, 6, 7. Okay. So we can draw 7 boxes here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And the last one is 7. So basically, our magnetic quantum number is telling us how many possible orbitals are there. Because remember, azimuthal gave us the shape, and this tells us in what orientation can they be. So for example, you can think that here the spherical orbital, right? So let's look at the first example. The first orbital, the s orbital, had the shape of a sphere. Okay. So there, even if you turn it around, it can have no different orientation. It will still look the same, right? Whether you turn it this way or that way. So we can't say a sphere in the x or y direction. That's why there's only one possible orbital. But if you look at the dumbbell, you could perhaps rotate it along the x-axis, y-axis or z-axis. So there could be 3 possible orientations. I'm giving you an idea, right? So that is why there can be 3 possible orbitals. And when you go to more complicated shapes, there are 5 possibilities, 5 possible orientations, 7 possible orientations, and so on. So as you're going into the higher subshell, there are more possibilities because the shape is becoming more complicated. So this is what is your magnetic quantum number, and its range is from -L to +L. So it depends on which subshell you're in. And as you can see, the number of orbitals keeps increasing, right? So it's 1, 3, 5, 7, and so on. So if you want to quickly predict how many orbitals are there in the subshell, what will be the formula? Very simple. So for L value of 0, there is 1 orbital. For L value of 1, you can see there is 3. So see, it is 1 orbital, 3 orbital, 5 and 7. So what is the formula going to be? The magic formula is number of orbitals is 2L plus 1, where L is basically your azimuthal quantum number, right? So it depends on your subshell number. So it is going to be 2L plus 1. And you can check and see, if you put L equal to 0, so you get 1. If you put L equal to 1, you get 3. L equal to 2, you get 5. L equal to 3, 7, and so on, right? So important formula that you can easily get the number of orbitals in a subshell is going to be 2L plus 1. So as we discussed, the magnetic quantum number M gives us the orientation of the orbitals. So what does this look like? So as we have discussed, the s orbital is spherical in shape. It has the shape of a sphere. So its orientation is only one possible, right? You cannot say it's oriented towards the x or y or z axis. So that is why here the only possible value of the quantum number M is 0. Now when we look at the p orbital, where L equals 1, so p orbital means L equal to 1. If you look at this, it is having the shape of a dumbbell. So dumbbell can have different orientations. For example, here you can see the dumbbell is aligned along the y-axis. Here it's along the z-axis. Here it's along the x-axis. So I can give different numbers here, like azimuth, the magnetic quantum number of 0. This is, let's say, plus 1. This is minus 1. So see, it is basically this quantum number, the magnetic quantum number, is giving us the orientation of your orbital, in which direction it is. And similarly, you have the d orbital. In the d orbital, remember, the azimuthal number is 2. And this is the shape of a double dumbbell. So now more complicated shape means more possible orientations. So as an example, you can think all these different orientations along the x, y, z will have different magnetic quantum numbers. So it's going to be like -2, -1, 0, 1, and another orientation can be possible, which is +2. So remember, it will take on values from -L to +L. Okay, so this is the 3D or the visualization of what is the meaning of magnetic quantum number. It is representing the orientation, in which direction your orbital is in. So far we have looked at three quantum numbers: the principal quantum number, the azimuthal quantum number, and the magnetic quantum number, denoted by n, l, and m respectively. So what are the possible combinations of these quantum numbers? Let's take a look. So n is our principal quantum number. Remember, it can take positive values like this, 1, 2, 3, and so on. So let's start with 1, which is representing the size, right? The principal quantum number represents the size, so the small size orbital, or you can say that's the shell number. For that, what is the possible values of L? L will take on values from 0 to n minus 1. Remember, this goes in the range of, L goes from 0 to n minus 1. So that's why there's only one possibility, 0 here. And what are the possibilities of M? M goes from plus L to minus L. So the only possibility here is 0. So what are the possible orbitals in the first shell? So this is the first shell. It has one subshell, the S subshell, which has only one possible orientation, right? Or you can say only one possible orbital. So the only possible combination is 1s. Next, when we go to the second shell, shell number 2, how many possible subshells it has? It has two possible subshells, 0 and 1. So 0, 1, which we denote as S and P. And in these subshells, so if you look at the 0th subshell, it has only one possible magnetic quantum number, which is 0, right? So only one possible orientation. And 1, which is the P subshell, it has minus 1, 0, 1. That means three possible orientations, so three possible orbitals. So we can say this represents 2p, right? This is combination of 2 and p is your 2p, 2 and s is your 2s, and 2p has three possible orbitals in it. Okay, so 1s has only one possible orbital in it, 2s has only one possible orbital, 2p has three orbitals in it. Similarly, we can go on in the third shell. These are the three possible subshells, S, P, D, or denoted by 0, 1, 2. And once again, in them, these are the possible orientations or orbitals. So 0, so 3s has only one orbital with it. 3p has again three possibilities, and 3d has five possibilities, minus 2, minus 1, 0, 1, 2. So you guys can note down this summary, and now you will start understanding that what are these quantum numbers. Again, they are giving you the address of where the electron is located, so which orbital it is located in. Similarly, you can make the same map for 4, the fourth shell. So if you look at the fourth shell over here, once again it has 4 possible subshells, because number of subshells equals to the shell number, S, P, D, F, or 0, 1, 2, 3, those are your quantum numbers, and these are your possible orientations or your orbitals. So 4s represents one possible orbital, 4p represents three possible orbitals, 4d represents 5 possible orbitals, and 4f represents 7 possible orbitals. So you guys are getting the picture that where are the places in the shell, in the subshell, in what orientation can these electrons spin? This is exactly the information quantum numbers is conveying to you, the address of where it is most likely to find the electron. To revise the concept, let's try out this question. So we've been asked how many subshells and orbitals are there in the second shell and third shell. So what are we talking about? If I represent n, the principal quantum number is the shell number, we've been asked about the second shell and the third shell. And they're asking us how many subshells are there. So remember, subshell is represented by our azimuthal quantum number, L. And what is the rule? L goes from n minus 1 to 0. So what are the possibilities here? L can take a possibility of 0 or 1, because you know 0 represents S and this is the P subshell. Or you also know that the number of subshells in a shell equals to the shell number, which is 2. That's absolutely correct. See, it has 2 possible subshells. What about shell number 3? It will have 3 possible subshells with these quantum numbers, right? So this is your S, P, D, right? And if we ask about how many orbitals, orbitals means we need to look at the third quantum number, the magnetic quantum number. So we need to look at M over here. So how many orbitals will be there? Remember, we had this formula, the number of orbitals is 2L plus 1. We can directly work it out. But let's write them down just to understand. So what are the possibilities here? For 0, it will have only the value 0. In 1p or in p, you will have basically values -1, 0 and 1. So can you see here how many possible orbitals in this subshell? So in this subshell, there will be 2 times 0 plus 1, so 1, and this will have 2. So we can see that the number of orbitals present here are total 1 plus 3, which is 4. We are getting 4 orbitals. Similarly, if you look at this one, what are the possible values of the quantum number m? So this will have 0, this will have -1, 0 and 1. This is going to have -2, -1, 0, 1 and 2. So total how many orbitals we have over here? 1, 2, 3, 4, 5, 6, 7, 8, 9. If we add all of them up, you can see we are having 9 possible orbitals. So you can see we are getting some interesting formula here that the number of orbitals present in a shell is actually equal to n square. So this is very interesting that the number of orbitals in a shell is actually working out to be n squared. You might have heard that rule, right? 2n squared, the Bohr-Berry's rule. This is where it comes. So the possible rooms for the electrons or the possible orbitals is actually equal to n square, where n is your shell number. So you can give the direct answer. You don't even have to work this out, but I've just shown you, for your understanding. You can directly say, oh, it's the second shell, 4 orbitals. 1, 2, 3, 4. It's the third shell, total 9 orbitals. It is 3 square. So simple. So we have looked at the first 3 quantum numbers. Now let's look at the last one, the easiest one, which is called the spin quantum number, denoted by the letter S. What information is this telling us? Spin quantum number is telling us that how the electron is spinning about its own axis. Because the first 3 were telling us the address of the electron, which room or which orbital it is in, right? But now an electron can be spinning in a clockwise or anti-clockwise direction about its own axis as it is revolving around the nucleus. So just like the earth is going around the sun and it is spinning around its axis, same thing for the electron. It is like the earth. Now the electron can have 2 possible spins, clockwise and anti-clockwise. And we denote this quantum number with the letter S, and we can say that plus half represents clockwise and minus half anti-clockwise, or vice versa. So whatever convention you want to use. So let's say I take plus half to be the clockwise direction, then I'll label minus half as anti-clockwise. Or whatever is given in your book, there's no standard convention here. It is just denoting clockwise and anti-clockwise rotations of the electron. And the electron can have only 2 possible rotations, clockwise and anti-clockwise, which is represented by the spin quantum number. So those are your 4 quantum numbers describing the first 3 describe the address of the electron, and this describes in which direction it is spinning. We have talked about the 4 quantum numbers. Now let's look at the very important Pauli's exclusion principle, which is given by the scientist Pauli. So what does this exclusion principle say? It states that no two electrons can have the same set of 4 quantum numbers. That means no 2 electrons can have the same address. That is, all the same quantum numbers cannot be the same. And remember, we discussed that there are 3 quantum numbers giving us the address n, l and m, and then you have the spin quantum number, which tells us is the electron spinning about its axis in the clockwise or anti-clockwise direction. So let's understand his exclusion principle with an example. So let's say if I tell you that a certain electron is there in, let's say, shell number 1, right? And it is in subshell number 0. It is having a magnetic quantum number of 0. So 1, 0, 0. And let's say its spin is clockwise, plus half. Then if you have another electron in exactly the same shell, subshell and its orbital, then it must have one thing different. So this has to be minus half. If you write this also as plus half, this is wrong, because according to Pauli, this is not possible. That means no 2 no electrons can have the exact same address. This is like everything is the same about them. But he said, no, electrons are exclusive. That is why it is the exclusion principle. So this must be minus half. Something must be different here, right? Or maybe if this was plus half, then one of these numbers needs to be different. Let's say we are talking about the electron in the second shell, right? And this can be 0, this can be 0, this can be plus half. So these guys are fine because here the shell number is different, right? Or maybe the subshell number is different, but something has to be different. So in another way we can think, Pauli is basically telling us that if n, l and m are the same, that is if the address are the same, that is the location of the orbital is the same, then how many electrons can the orbital have? That's right, the answer is only 2. Because there are only 2 spins possible for the electron, either clockwise or anti-clockwise. No other spin is possible. So basically every orbital, Mr. Pauli is telling us that every orbital or any orbital that you consider can hold maximum of 2 electrons. That's it. And that's why whenever we represent an orbital like this as a box or a room, we can only put in 2 electrons, one with a plus half and one with a minus half. That's it. No other electrons are possible. So now you can understand that when I drew that house, right, when I drew that house analogy, see, this is why when I was filling up the rooms, I said there can be only 2 fellows in the room, only 2 electrons, the one on the left hand side and right hand side we called it, but it is really the clockwise and anti-clockwise spin. And this is exactly what Pauli was describing us. So every time you represent electrons, there are only 2 possibilities. So similarly, when we looked at these orbitals, we can only fill it with 2 electrons each, not more than that. That's it. You can just keep filling it with 2 electrons in each and every orbital. So if we want to know the number of electrons in a shell, how much is it going to be? We said that the number of orbitals in a shell is equal to n squared, the total number of orbitals, right? We just discussed that because the first shell can have 1 orbital, second shell can have 2 square orbitals, and every orbital can have 2 electrons. So that is where you get the formula that you have learnt in Bohr-Berry's rules, 2n square. So let's write that down, that the number of electrons in a shell, from Pauli's exclusion principle, the number of electrons in a shell equals 2n square. That's it. Because every orbital can have maximum 2 electrons, and in a shell, nth shell, there can be total n square orbitals as we saw. So remember, quantum numbers are giving us the location, the address where we will most probably find the electron. And you can easily remember these quantum numbers with this house analogy that I gave you. So remember, it's like having these houses for the electrons. So this is your first house, which represents shell number 1. This is the second house. And once again here, we are going to split the subshells or the levels into rooms. And you can do the same thing here. And remember, in each and every room, how many electrons can you have? That's right, 2 electrons according to Pauli's exclusion principle. So you can just put 2 electrons in any of these rooms. And so the house number, the level, right, the room number and the spin gives you the full details about the electrons. So you can easily remember it with this simple house analogy that will help you understand what is this concept of shells, subshells and orbitals, and we discussed the spin of these electrons. So hope the concept of quantum numbers was very clear to you. And now let me ask you an interesting question. Can you calculate how many subshells, orbitals and electrons are there in the 4th shell? So once again I repeat, can you calculate for me that in the 4th shell, how many subshells are there, orbitals and electrons? And do let me know your answers by putting it in the comments below. I look forward to your answers and I promise to reply to them. So friends, in maths you've heard of natural numbers, whole numbers, real numbers, and now in chemistry you know what are these quantum numbers. So I hope you'll remember that house analogy that we did, and how these quantum numbers can help describe the location of where the electron will most probably be found. So if you like this video, don't forget to hit the like button and share it out with your friends, because sharing is caring. And if you haven't subscribed to our YouTube channel yet, come on, what are you waiting for? Smash that subscribe button and click on the notification bell and select the all option so that you don't miss out on any of our exciting videos. And do check out the courses on our website manochaacademy.com and our Android app Manocha Academy, because we have full courses on physics, chemistry, biology, maths, coding and artificial intelligence. In these courses, you're going to get live classes, interactive videos, quizzes, questions, mock tests and revision notes. So guys, what are you waiting for? Do check out the links given below and share it with your friends. So stay connected with us and just keep learning.